Have you ever, like, looked at one of those stunning, highly detailed 3D digital models of a new building before it's actually built?
Oh, yeah, you know the ones where you put on a VR headset or stare at a big monitor.
Right, exactly. And you can virtually walk through the lobby, and you see the afternoon sunlight hitting the polished concrete floors.
You can practically feel the brushed metal texture on the door handles. It looks so real.
It really does. And you look at a rendering like that and naturally assume, well, they have every single thing figured out, down to the last millimeter.
But under the hood, I mean, a terrifying percentage of the parts in that beautiful digital environment might just be rough placeholders.
Yeah, which is wild to think about. So when you have architects, structural engineers, plumbers, and electricians all looking at the exact same 3D model, how do they know what is real and what is just a pretty guess?
Right, and more importantly, how did they avoid a catastrophic multi-million-dollar collision on the actual construction site?
Exactly. Because if they don't know, it's a disaster waiting to happen.
It really is. It basically comes down to establishing a strict baseline of reliability. Like, if an electrician looks at a digital model and assumes a heavy conduit is going to be mounted exactly flush against the ceiling.
But the mechanical engineer, they only put that conduit in the model just to say, like, some kind of wiring goes generally in this room.
Yes, the physical reality is going to be a complete mess. The moment the contractor tries to install the adjacent ventilation system, they just run out of physical space.
Right, and work stops. Materials have to be reordered, schedules are completely blown.
This costs everyone a fortune, yeah.
And avoiding that disaster is really the mission of today's deep dive. We are exploring the latest LOD specifications.
Which is essentially the secret language of building information modeling, or BIM.
Yep, BIM. We're going to decode how massive, highly complex project teams actually agree on what a digital model represents at any given moment.
It's basically the framework that ensures everyone, from the lead architect designing a skyscraper to the contractor pouring the concrete, is working from the same standard of truth.
Okay, let's unpack this. Because to understand how builders communicate using these LOD specifications, we first have to clarify what those three letters actually mean.
Oh, for sure. It is an incredibly common trap to mistake it for something entirely different.
Right, if you are casually orbiting the construction, tech, or design world, you probably assume LOD stands for level of detail.
Most people do. But according to the LOD specifications, that assumption misses the entire point of the system.
So what does it stand for?
LOD stands for level of development. And, I mean, the gap between detail and development is massive.
It's a huge difference. Let's dig into that distinction. Level of detail is essentially a measure of graphical complexity, right?
Exactly. It's how much visual stuff is crammed into the digital model.
Like, does the digital office chair have 5 individual casters and a textured mesh back? Or does the brick wall show the individual mortar lines?
Right, that is detail. Level of development, however, measures the degree to which that element's geometry and physical properties have actually been thought through and finalized.
So it's purely a measure of reliability.
Yes, 100%. It's about how much you can trust the model.
Let me float an analogy to separate these two ideas because I think it helps. Imagine someone hands you a map to a completely fictional place, let's say the lost city of Atlantis.
Okay, I'm with it.
The artist who drew this map went all out. It is full color, beautifully shaded, and you can see individual cobblestones in the streets and snowcaps on the mountains.
So that map has a profoundly high level of detail.
Right, but it has an absolute zero level of development. You cannot rely on it to navigate the real world, to find a grocery store or drive a car.
Because the place doesn't actually exist.
Exactly. Now contrast that with like a quick, messy napkin sketch your friend draws to show you how to get to the airport.
Oh, I see. Low detail, but highly developed because it actually gets you to your flight on time.
Yes. The Atlantis map versus the napkin sketch.
That is a great way to look at it. And the LOD specifications make this concept explicitly clear with a really fascinating rule.
Oh, the cumulative rule, right?
Yeah, LOD requirements are minimums, and they are cumulative. An element in a 3D model can look incredibly realistic. It can have a staggering level of detail. But if its actual location in the physical building is just a wild guess, it is stuck at a very low level of development.
A beautifully rendered lie is still a lie.
Exactly. It's a visual trap. People are psychologically wired to trust high-fidelity images.
Oh, for sure. If it looks real, we assume it is real.
Right. When a client or a junior engineer sees a photorealistic pump in a model, they just assume its dimensions are final.
Which is super dangerous.
It is. The LOD specifications exist to force project team members to ask, like, can I use this specific digital object to order $50,000 worth of materials?
Or can I use it to coordinate a complex heating system?
Yeah.
Or is it just an Atlantis map taking up space?
Exactly.
So if I am on that construction site, how do I actually know if I'm looking at a fictional map or a reliable one? There has to be a way to score this reliability, right? A continuum we can measure against.
There is. The LOD specifications establish very specific, standardized milestones for exactly this reason.
And they operate on a scale, right? From LOD 100 up to LOD 500.
Yep, marking the journey from a vague idea to an undeniable reality.
Okay, let's walk through this continuum, starting at the genesis of a project, which is LOD 100. The specs call this the space reservation phase.
Space reservation. It is purely conceptual. We aren't looking at a recognizable shape yet.
Right, it might literally just be a digital volume or a solid mass
Mm.
that tells the team, something goes here.
Think of it as a 3D bubble. A perfect example is a cooling tower for a commercial building.
Oh, that's a good one.
Yeah, the engineering team might not know what brand of cooling tower they are going to buy yet. They don't know the exact dimensions or where the water intakes are located.
But they absolutely know they need a massive piece of equipment on the roof.
Right. So they drop an LOD 100 block into the model that just represents, say, 500 cubic feet of space.
And that matters, because even if the architect doesn't know the brand, the structural engineer needs to know that a 10,000-pound box of metal and water is going to sit on that specific section of the roof.
Exactly. They have to put columns underneath it early in the design process.
Okay, so that's LOD 100. Where do we go from there?
From there, the design matures into LOD 200. This is what they call the generic placeholder.
So it's starting to look like a real object now.
Yeah, the element now has recognizable 3D geometry. If it's a pump, it roughly looks like a pump.
But I'm guessing you still can't totally trust it.
Right. The specifications mandate that any information derived from it, like its exact size, shape, and location, must be considered approximate.
It's basically the digital equivalent of a rough sketch.
Yeah.
You recognize the object, but you'd be crazy to use a ruler on that sketch to, cut a piece of expensive steel.
That would be a very expensive mistake. But then the project hits LOD 300, which is the accurate measurement level.
Okay, so things are getting locked in here.
Yes. At LOD 300, the size, shape, and location are exact. They are absolute, located precisely within the model's coordinate system.
So the volume of that cooling tower we talked about is no longer a guess. It reflects the actual manufacturer's dimensions.
Exactly.
But I want to pause on LOD 300 because there's a really fascinating note in the LOD specifications about this level. It states that designers rarely generate model elements past LOD 300.
Yeah, that surprises a lot of people.
Right. Why would the person designing the building stop there? Like if the architect knows the exact size of the air conditioning unit, why wouldn't they just model how it physically attaches to the ceiling so the construction crew knows what to do?
Well, it comes down to a mixture of legal liability and highly specialized trade knowledge.
Oh, liability. That makes sense.
Right. An architect or a lead mechanical engineer designs the intent of the building. They specify that a space needs a certain volume of cold air, and they select a unit capable of delivering it.
But they aren't the ones actually turning the wrenches.
Exactly. They are not licensed tradespeople. They don't know the exact proprietary metal hanger the local plumbing subcontractor prefers to buy from their supplier.
Or the specific welding technique the fabricator will use in their shop.
Yes. So they hand off the model at LOD 300 and basically say, here is the exact unit, and here's exactly where it goes. You figure out how to bolt it to the concrete.
Wow. Okay, so the designers stop at 300, which introduces LOD 350.
Yes. LOD 350 is the coordination level. This is where the digital model becomes a manual for physical construction.
So it's not just the object anymore.
No, LOD 350 shows the interfaces with other systems. It requires the contractor's craft knowledge to model the actual clearances, the custom supports, and the structural connections.
And that naturally brings us to LOD 400. The specs call this the fabrication level.
Yeah, fabrication. The specs say this is detailed enough for shop drawings.
Meaning it has all the supplementary components required for actual fabrication and field assembly.
We are talking about modeling the individual nuts, bolts, and welds.
Which sounds exhausting. Just so you can pre-assemble a custom piece of ductwork in a warehouse before trucking it to the site.
It is exhausting. The effort required for LOD 400 is so intense that most building models contain very few LOD 400 elements.
Really, they just reserve them for highly custom, pre-manufactured pieces.
Exactly. Pieces that have to slot perfectly into the building upon arrival, like a puzzle piece.
Okay, well, I have to push back here on the final level then, because if LOD 400 has every nut, bolt, and weld perfectly modeled and ready to build, what could LOD 500 possibly be?
I get this question all the time.
Do we model the microscopic grain of the steel? I mean, how do you get more developed than ready to physically build?
It's a completely logical question, and honestly, a very common misconception in the industry. LOD 500 is not a higher level of detail than 400.
It's not, so it doesn't mean zooming in closer.
Not at all. Instead, LOD 500 represents a fundamental shift in the nature of the information.
Okay, I'm listening.
The LOD specifications state that LOD 500 indicates the element's geometry is determined through the observation of an existing as-constructed item.
Oh, so we are no longer designing the future. We are recording the present.
Exactly. You step out of theory and into reality.
So like a team actually goes out to the physical construction site.
Yes, they go out, measure or laser scan the pipe that was actually installed by a human being, and update the digital model to reflect what exists in the physical world.
That is brilliant.
The LOD 500 definition requires that the model element's level of accuracy be explicitly noted, providing a true as-built record.
So whoever has to maintain that building for the next 50 years actually knows where the pipes are hidden behind the drywall.
Precisely.
It's the ultimate reality check. The progression makes perfect sense in theory, but to really grasp the mechanical power of this framework, we should apply these rules to actual steel, concrete, and pipes.
Let's do it. Let's look at how the LOD specifications dictate the rules across different building disciplines.
Okay, well, architecture is often the easiest place to start because it forms the visible shell of the project. Let's look at exterior enclosures, specifically roofing.
Good example.
If a design team is operating at LOD 100 for a roof, the LOD specifications say the model might just be a solid mass representing the overall building volume.
Right, or it might be schematic wall elements that aren't even distinguishable by type or material.
It is just a geographic marker saying, this volume represents the top of the building.
Now, compare that to structural engineering, which demands a much higher degree of spatial certainty early on. Let's examine structural masonry.
Like a heavy, load-bearing concrete block wall.
Yes. When that masonry wall reaches LOD 300, the specifications state that the digital model must include planned openings at nominal dimensions.
Meaning you have the wall's overall thickness and height, and you have the basic geometric holes where the doors and windows will eventually go.
Right. But push that exact same masonry wall to LOD 350, and the amount of craft knowledge required is just staggering.
Really? How so?
Well, you don't just have basic holes anymore. You must model actual penetrations to rough openings.
Okay.
You have to include the dowels connecting the wall to the foundation, the reinforced bond beams running through the blocks, and crucial elements like expansion joints.
Let's hover on expansion joints for a second because that sounds like a tiny detail, but it has massive physical consequences.
Oh, huge consequences.
What is the mechanism there? Why does an expansion joint matter so much at LOD 350?
So concrete and masonry expand and contract depending on the temperature. Right. An expansion joint is a literal physical gap left in the concrete.
It's usually filled with some kind of flexible material.
Exactly. So the building can swell in the summer heat without cracking the entire foundation.
Okay, I see where this is going.
If a masonry wall model at LOD 300 doesn't show that gap, a plumber might look at the wall and decide to run a rigid copper water pipe straight through that exact spot.
Oh, man. And when summer hits, the concrete expands, the gap closes.
And the building literally shears the rigid pipe in half,
creating a catastrophic water leak entirely because the model lacked LOD 350 development.
Exactly. The plumber relied on a model that wasn't ready to be relied upon.
Which perfectly sets up the third discipline, MEP, mechanical, electrical, and plumbing.
This is where it gets really complicated.
Oh, yeah. According to the specs, at LOD 200, a domestic water pipe or an electrical raceway is just an approximate shape.
It's essentially an empty digital envelope showing roughly where things will run.
Right. Then, at LOD 300, it evolves into the specific design specified size. A 4-inch pipe is modeled as a 4-inch pipe.
Yes, but you only have to include approximate allowances for the clearances needed for supports.
Right, but step up to LOD 350 for that same pipe, and the requirements just explode.
Oh, absolutely. You have to model the actual size, shape, spacing, and location of the pipe, the valves, the fittings, and the insulation.
But the most critical aspect is that you must model the actual clearances required for all hangers, supports, and specialized elements, like vibration and seismic control.
Seismic control. So you aren't just modeling the physical pipe. You are modeling the empty space around the pipe.
Yes. Empty space is arguably the most valuable commodity on a construction site.
It really is, because a rigid pipe carrying high-pressure water physically vibrates. It experiences water hammer when valves close.
And in earthquake-prone areas, it legally must have room to sway without hitting anything solid.
Right, so if you only model the 4-inch pipe, an electrician might come along and install a massive tray of server cables right next to it.
Because the model made it look like there was empty space available.
Exactly. But in reality, that empty space was reserved for the pipe's seismic sway.
So when the pipe shakes, it smashes into the cable tray, potentially destroying critical infrastructure.
And that is the magic of LOB 350 right there. It's not just about clash detection and finding out where a digital pipe hits a digital wall.
It's about clash avoidance.
Building the empty space into the model so the human beings on site don't make assumptions that lead to disaster.
Wow. So why go through the agonizing trouble of defining a single pipe hanger or the empty air around a vibration control valve at LOD 350?
Because on massive, complex projects, assumptions cost millions of dollars and blow up schedules.
It's about protecting the project from the psychology of guessing.
Exactly. The LOD specifications act as an objective baseline for communication. It strips away the ambiguity.
But there is a vital caveat in the executive summary of the documents regarding how teams even talk about these models.
Oh, I know exactly what you're referring to, and it blew my mind the first time I read it.
The specs explicitly state there is no such thing as an LOD 300 model.
It is a fundamentally flawed request, yet project managers ask for it constantly.
Send me the LOD 300 model by Friday.
Yes, all the time.
But why is that a flawed request? If the design is finished, shouldn't the whole model be at LOD 300?
Well, because a building is not a single unified object. It is a collection of thousands of mini projects, all progressing from concept to precise definition at completely different speeds.
That makes a lot of sense.
Yeah, when the structural foundation is fully finalized, engineered, and actively being poured on site, meaning it's operating at LOD 400 or even LOD 500, the interior custom lighting for the lobby might still just be a conceptual LOD 100 bubble taking up space.
Because the structural engineer moves faster than the interior designer.
They have to. You can't build a roof until you pour a foundation.
Right.
Therefore, a project model always contains a mix of different LODs at any given time.
The framework doesn't dictate who models an element or exactly when they do it.
No, instead it allows a project team to identify exactly what level of reliability is expected from every specific component at a specific milestone.
It's basically a design work plan. It allows a plumber to click on a pipe and know instantly, is this just the architect's fantasy or is this the finalized engineering plan I need to order materials against?
Exactly. It takes the chaos of thousands of overlapping tasks and transforms it into a predictable, manageable workflow.
In any collaborative environment, people depend on other people's work to move their own work forward.
And friction and failure occur when someone makes a hard decision based on soft data.
I really want to connect this directly back to the listener right now. You might not be building a 100-story skyscraper.
Probably not.
But whether you are managing a massive software deployment, organizing a cross-departmental marketing project at your company, or, frankly, just trying to get a straight answer out of a contractor remodeling your kitchen,
Establishing a shared framework for minimum standards of reliability is an absolute superpower.
it forces transparency. It requires every stakeholder to define what they actually know as a proven fact versus what they are still just guessing at.
It stops people from making final, expensive decisions based on what are essentially digital placeholders.
It forces teams to confront the difference between how detailed something looks and how developed it actually is.
Which is the fundamental question that should drive any major collaborative effort, really. Are we making decisions based on detail, or are we making decisions based on development?
Detail versus development. It's so crucial. So to wrap up our journey today, we've traveled from the vague conceptual space reservation bubbles of LOD 100 all the way to the highly specific field-verified realities of LOD 500.
We really covered the whole spectrum.
We did. And we've seen how establishing a shared, highly rigorous language across architecture, structure, and MEP ensures that a beautiful 3D digital rendering doesn't just stay a pretty picture.
It ensures that the digital intent actually translates into a functional physical reality.
Without the agonizing delays of a million-dollar collision along the way.
Exactly. And, if architects and engineers have figured out how to standardize the reliability of a massively complex 3D building so that thousands of different tradespeople can collaborate without disastrous errors, what other areas of your life or work could benefit from an LOD system?
That's a great question to leave on.
Yeah, next time someone hands you a piece of supposedly factual information, a flashy business projection, or a heavily designed slide deck, ask yourself, is this an LOD 100 placeholder just taking up space, or is it an LOD 500 field verified reality?
Because at the end of the day, a stunning, highly detailed picture of the future is incredibly dangerous if half the parts are just rough placeholders. You have to know what you can actually rely on.